Okay, in this video we're going to start Chapter 6. Chapter 6, Section 1 is Slope Fields and Euler's Method. And actually we will not be going over Euler's Method. That's not a topic on the Calculus AB test. It is on the BC version, but we won't be doing that in this class. We're going to use initial conditions to find particular solutions to differential equations. We're going to look at slope fields to approximate solutions of differential equations. And again, Euler's method is not going to be covered. So in this text, you will learn that physical phenomena can be described by differential equations. Recall that a differential equation in x and y is an equation that involves x, y, and one or more derivatives of y. In the next section, you're going to see problems involving radioactive decay, population growth, and Newton's law of cooling can be formulated in terms of these differential equations. A function, y equals f of x, is called a solution of a differential equation if the equation is satisfied when y and its derivatives are replaced by f of x and its derivatives. For example, differentiation and substitution would show that, here's an equation, y equals e to the negative 2x power, is a solution of the differential equation, y prime, or the derivative of y, plus 2 times y, the original y equation, is equal to 0. You know, if we took the derivative of this, it would be e to the negative 2x, and by the chain rule times a negative 2. So we'd have negative 2 e to the negative 2x. So that would go in for this y prime. And 2 times the original equation, e to the negative 2x, would be 2e to the negative 2x. So we'd add those and get a 0. It can be shown that every solution of this differential equation is in the form y equals c, some constant, e to the negative 2x. Where c is any real number. This solution is called the general solution. Some differential equations have singular solutions that cannot be written as special cases of the general solution. Such solutions are not going to be part of this text. The order of a differential equation is determined by the highest order derivative in the equation. For instance, y prime equals 4 times y is a first order differential equation. First order linear differential equations are discussed in section 6.4 of this book. Two chapters ago in section 4.1, example 8, you saw the second order differential equation s double prime of t, that's the second derivative of our position function, was equal to negative 32, had this general solution. So we would anti-derive twice to get the position function. It would be negative 16t squared plus c sub 1 times t plus c sub 2. This contains two arbitrary constants, the c sub 1 and c sub 2. It can be shown that a differential equation of order n has a general solution with n arbitrary constants. Here in example 1, we're going to verify a few solutions. Determine whether the function is a solution to the differential equation y double prime minus y equals 0. So we're going to look at part A here, y equals sine of x. What is the first derivative of sine x? Well, derivative of sine is cosine x. And for our differential equation, we're going to need the second derivative, y double prime. Well, what's the derivative of cosine? Negative sine x. And we want to check those in this differential equation, y double prime minus y equals 0. So first I'm going to plug in my second derivative that I just found, negative sine x, minus y, the original equation, sine x. Does that equal 0? Well, negative sine x minus sine x, we add the opposite, and we get negative 2 sine x equals 0. No, that's not true. So y equals sine of x is not a solution. So we checked out the first one, not a solution. Let's take a look at part B. Y equals 4e to the negative x. The first derivative, y prime, would be, well, the derivative of e to the x is e to the x, and here it'd be 4e to the negative x. And then the chain rule says we would take the derivative of the inner function, or here it's the exponent. The derivative of x is negative 1. So that would put a negative down in front of our 4. And when we took the second derivative, the same thing's going to happen. it is its own derivative, negative 4e to the negative x. And then the chain rule again would say, well, you got to take the derivative of that inner function, and that is a negative 1. That would turn this to a positive. So we go back to the same differential equation, y double prime minus y equals 0. Well, here's our second derivative, 4e to the negative x, minus our original y equation, 4e to the negative x. Well, the exponential base, or the exponentials are the same, so it's just 4 minus 4. That would be 0 e to the negative x. And of course, 0 times anything is 0. So this is a solution. Y equals 4e to the x is a solution. All right, one more to go. And this looks pretty similar to what we had in B, but now instead of a 4, there's just a c there. And you know, c is just a number. It's a constant. Y equals c e to the negative x. Oop, well, it's positive x. C e to the x. So the first derivative, y prime, would be c e to the x. And the second derivative would be c e to the x. Plug that into the given differential equation, y double prime minus y equals 0. Well, the second derivative is right here, c e to the x, minus the first equation, our original equation, is c e to the x. Well, that minus itself is equal to 0. So c e to the x is a solution. Geometrically, the general solution of a first-order differential equation represents a family of curves known as solution curves, one for each value assigned to that arbitrary constant. For instance, you can verify that every function in this form, y equals that constant over x, is a solution to the differential equation x times y prime plus y is equal to 0. The figure below shows 4 of the solution curves for different values of c. You know, here the darker one is when c is equal to 1, and the same down here. And then we have c equals to 2 in the lighter gray. And we have other ones in blue for negative values of c. As discussed a couple chapters ago, particular solutions of a differential equation are obtained from given initial conditions. These give the values of the dependent variable or one of its derivatives for particular values of the independent variable. The term initial condition stems from the fact that often in problems involving time, the value of the dependent variable or one of its derivative is known at the initial time t equals 0. For instance, the second-order differential equation, s double prime of t equals negative 32, having the general solution, you know, there's our position function s of t, negative 16t squared plus constant 1 times t plus constant 2, might have the following initial conditions. For the first derivative, 0 is equal to 84, s prime of 0 is equal to 64, and we have our initial condition for the position function itself, s of 0 equals 80. In this case, the initial conditions would give this particular solution. You know, we could solve for the constants, and the 64 would go in place of constant 1, and the 80 would go in for the second constant, and there is our particular solution. In example 2, we're going to find a particular solution. So for the differential equation, x times y prime minus 3y is equal to 0, verify that this, y equals constant time, or x to the third, is a solution, and find the particular solution determined by this initial condition, y equals 2 when x equals negative 3. Now they can word this in a few different ways. Here they're saying determined by this initial condition, y is 2, x equals negative 3. They could have said, given this point is on the curve. They could have worded it that way and gave you this. Our x value is negative 3, our y value is 2. That is just a point on in the Cartesian plane that happens to be on the particular solution that we're looking for in this differential equation. So the first thing they want us to do is verify that this is a solution to the differential equation. So they gave us y equals cx to the third. And in our differential equation, we have a y prime. So we have to derive. So when we use the power rule on this, the 3 is going to come down and multiply by the c. So we're going to have 3c, and then drop the power by 1, x squared. So that's our first derivative, and we want to go to that given differential equation, xy prime minus 3y is equal to 0. And we just want to plug in our y and y prime that we just found. So x, and then y prime is 3c x squared. 3 times that constant, x squared. And then we have minus 3 times y. And the original equation was cx to the third. That was our y value. Does this equal 0? So here we would sort of distribute the x. We could even just distribute it right to, we have an x squared already. X times x squared is x to the third. So we have 3c x to the third. That's an ugly third. Minus here, we'd just distribute the 3 there, and we'd have 3c x to the third. Does that equal 0? Yes, it's 3c x to the third minus itself. That does in fact equal 0. So we did verify that that is a solution. Now we want to find the particular solution given our initial condition. So let me clear this out of here. We have our general solution, y equals cx to the third. This is our general solution. So c is just our constant. That's what we're going to solve for. We're going to plug in a value for x. -3 goes in for this x. -3 to the third power. And for the y value, we put in a 2. So we have 2 equals c times -3 quantity to the third is -27. And to isolate c, we divide by -27. C is going to equal -2/27. So we solved for the constant. Now just to find the particular solution, we take this value for the constant, and we're going to plug it back into the general solution. So y equals, instead of that c, we can write -2/27 x to the third. Or you might see it written, with that x to the third completely in the numerator. That's the exact same thing. And then you'd have x to the third. Yeah, that's it. -2/27 x to the third is the particular solution. A little note here. To determine a particular solution, the number of initial conditions must match the number of constants in the general solution. Okay. Now on to slope fields. Solving a differential equation analytically can be difficult. Sometimes it's even impossible. However, there's a graphical approach you can use to learn a lot about the solution of a differential equation. Consider a differential equation of the form y prime is equal to f of x comma y. And all this is saying is, remember, a derivative is just a slope. So we have a slope going on here, and that slope is determined or defined in terms of the x and y coordinate of that point. So it says here where f of x comma y is some expression in x and y. At each point, x comma y in the xy plane, where f is defined. The differential equation determines the slope y prime is equal to f of xy of the solution at that point. If you draw short line segments with the slope f of xy at the selected points in the domain of f, then these line segments form a slope field or a directional field for that differential equation. Each line segment has the same slope as the solution curve that would pass through that point. A slope field shows the general shape of all the solutions and can be helpful in getting a visual perspective of the directions of the solutions of a given differential equation. Okay, here in example 3, they're going to have us sketch one of these slope fields. A real simple one, drawing a full one would be pretty time consuming. But sketch a slope field for the differential equation y prime equals x minus y. So the derivative at any point in the xy plane is given by its x coordinate minus its y coordinate. And they ask us to do this for 3 points. The first one is negative 1, 1. So negative 1, 1 is right here. And if we plug in our x coordinate, that's negative 1 minus our y coordinate 1. We add the opposite and get negative 2. The slope at that point is negative 2. And negative 1 would be downward at a 45-degree angle. So this is going to be a little steeper than that. The next point they want is 0, 1. 0, 1 is right here on the y-axis. So a 0 goes in for our x coordinate, y is 1, 0 minus 1 is negative 1. Downhill slope, but not as steep as our last point. This is down at about a 45-degree angle. And the last point they ask us for is 1, 1. So 1 goes in for x, minus 1 goes in for y. That's a slope of 0. So at this point, we would have a horizontal tangent line. And let's do a few more points, more than what they asked us to do. Let's hop down there and go right across the x-axis. So here's the point negative 1, 0. Negative 1 for x, 0 for y. And that turns out to be a slope of negative 1, just like this point. So downhill about 45-degree angle. The origin will be an easy one. 0 for x, 0 for y. 0 minus 0 is 0. Horizontal. The next point, 1, 0. 1 minus 0 is 1. So here we're going to have a slope uphill at about a 45-degree angle. And let's do another row. Negative 1, 2 would be right here. Negative 1 minus 2 would be negative 3. Nice steeper slope. Right on the y-axis, that would be 0, 2, or 0 minus 2, negative 2. Our next point would be 1, 2. 1 minus 2 would be negative 1, going downhill. So we're starting to get an idea. Each little point here has its own slope, and we mark that with just a little tiny line segment. And this is a slope field or a directional field. Alright, here in example 4, we're going to identify slope fields for some given differential equations. It's a little matching game. Here's 3 slope fields, A, B, C. Here are 3 differential equations, 1, 2, 3. Match them up. Now, if you want, pause the video and then try it yourself and then turn it back on and check your answers. So the first differential equation is the derivative y prime equals the x coordinate plus the y coordinate. The second differential equation, the slope y prime is just equal to the x coordinate. In part 3, the y prime, the slope is equal to just the y value. So let's see which one. Let's take a look at some of these slopes here, or some of these slope fields above. When I look at the first one, I notice on the vertical lines, it looks like all the slopes are the same. Here all the slopes are same downhill. Here they all look like we have the same slope going uphill. In graph C, I can sort of see something going on like that, but horizontally. Here I can see all the slopes are the same. Here I can see all the slopes are the same. But when I look up and down, I can see that they're changing. As we go up, they're getting steeper. As we go down, they're getting steeper to the negative side. B is the weirdest looking graph. Here there's nice and steep at the top, and as we go down, it flattens out. Down here, we're nice and steep downhill, and as we go up, we flatten out. We can almost see a line of these slope segments going diagonally that almost look like they're all horizontal, down like that. So let's match them up. The first one, the easiest one to do might be this. The slope is equal to the x coordinate. If I look at this x coordinate, all the lines should have a slope of 2 that are above or below. And I can see that as they go up, the slopes are changing, positives and negative. So that's not it. If we go back to the first graph, here my x value is 2, so this point would be 0, 2. It's got a slope of 2. This would be 2, 2. It has an x value of 2. The slope is still 2. All these slopes have a steepness of 2. If I look over on the negative side, here's x equals negative 1. So all points above or below that have this as their x coordinate should have a slope of negative 1. And it looks like they do. At the origin, x value of 0. Every point with an x coordinate of 0 will have a horizontal slope. So graph A goes with differential equation 2. The third differential equation, y prime equals y. The slope is equal to the y value. Here on the x-axis, all those segments are lying right on the x-axis. As we go up to a y value of 1 right here, all points that have this as a y coordinate will have that as a slope for their segment. As we go up to positive 2, all the points with a y value of 2 have that same slope. Same for the negative values, negative 2. So graph 3 goes with C. And of course, by the process of elimination, graph 1 will go with B. And this is where we get this weird diagonal going down through here. X plus y is equal to our slope, our derivative. So at 0, 0, the slope is 0. At negative 2x coordinate, positive 2y coordinate, negative 2, positive 2, we go up and we have that same horizontal line segment. Here at 2, negative 2, 2 plus negative 2 would be 0. So we have that diagonal of horizontal segments as we go down. And from there, it's the x coordinate plus the y coordinate. So we see sort of a pattern emerging as we graph out enough of those little line segments. Now this is not in the book. I found this elsewhere online. These are how to do directional or slope fields on your TI-89. These come in real handy for if you've run into one of these questions on the AP test or in the homework, and this even shows you how to find a particular solution. So we will go over that in class, or you can just follow along, look at these slides with your TI-89, pause the video, or these are right in your notes also. Try these problems out. Here in example 5, we're going to sketch a solution using a slope field. Now this isn't an exact science, you should get a good feel for it though. Sketch the slope field for the differential equation, y prime equals 2x plus y. Use the slope field to sketch the solution that passes through the point 1, 1. And there's a little note here, drawing a slope field by hand is tedious. In practice, slope fields are usually drawn with a graphing utility. So here is the slope field they're giving us for our given differential equation. Slope, or y prime, is equal to 2x plus y. And they want us to sketch the solution that passes through this given point 1, 1. So if we go over here and to here, this would be 0.11. We know that that is on our solution curve. Now how you sketch these is, you just sort of got to have a feel for it, and you got to think of these as more of a gravitational field. As you're sketching your curve away from your given initial condition point, every little line segment around you is sort of guiding your path. They have gravity that affects you, and as you get close to a point, as you get close to one of these segments, you assume the same slope that it has. So here the easy part is just going to be drawing up and away from our initial condition point here. We can see the little segments on either side of it are almost vertical going up, so we know that that's how that gravity is sort of going to pull our curve. Now we've got to get a different feel as we're going down this way, because we do see something odd's happening here with our little line segments. So let's start to figure out how that gravity would affect us. As we start coming down away from our point, we're going to get close to this segment and these segments here. We can see that slope is starting to level out as we come down farther. So let's see, as we come down here, our curve is going to have a slope in between there, so we can connect that point up. As we come down a little farther, we see here across our y-axis, we have slope steep, less steep, less steep. So it looks like it's horizontal right here, and here it's starting to go down a little bit. So as we come down, we're going to start to flatten out a little bit right around that origin and start to kick back here. And when we do, we can see these slopes are going to start to draw us back up this way. So as we start moving up here, this slope, or the slope of this curve sort of grabs us and starts moving us up in this way, and it looks like we're going to head up off into that direction. Again, it's not an exact science. If I pass, there will be one of these on a test or a quiz, and everybody's answer is going to be slightly different, as opposed to did you go above or below, this line segment right here? Were you above or below this one? It's just more of a feel for how those little segments are going to draw or influence your curve. Euler's method, again, it's not on the AP test for the AB part. It is a BC topic. If you're curious about it, read up here on Euler's method. It's more of an estimation technique, sort of relying kind of on what we were doing here with these slope fields, where as you go along, you just correct yourself as you go. So you're building this estimate, step by step as you go with an Euler approximation. It's an interesting technique, but not anything that I want to spend any time on for us getting ready for that AP test.